In a previous video note, we worked with a project taken from Objects First with Java by David Barnes and Michael Curling. We saw how to open a project, how to create an object via the class diagram, how to inspect the state of an object, and how to call the methods of an object. In this video note, we're going to use the Figures project and explore some more of the fundamental concepts that we will be using over and over again as we learn about object-oriented programming using the BlueJ environment. In particular, we shall learn about methods and parameters. Our first step is to open a project that we've used before. We can do this most easily via the Project Open Recent menu. Now we're going to create two square objects. Let's bring up inspectors on both of those squares. If we put them side by side, we can clearly see that the states of the two squares are indistinguishable. In fact, this is not unreasonable. If we think of a class as being like a blueprint or a template for creating instances, then creating two instances in an identical way is likely to produce identical instances. Just like items coming off a production line, they are to all intents and purposes identical. However, we must always keep in mind that each instance is an entity in its own right, independent of all other instances created from the same class. If we ask one of the instances to do something, it will have no effect on the other. We can see this in practice by calling some methods on one of the objects, but leaving the other one alone. Firstly, let's make one of them visible. The visualization window appears as before, showing a red square. Incidentally, the window is actually an instance of the canvas class that we can see in the class diagram, so we will sometimes call it the canvas window or simply the canvas. We have to be a little bit careful about identifying the square shown as being the first square because notice from the inspector that both squares have the same size and positions within the canvas, but the fact that the inspector shows that one is visible and the other invisible confirms that for us. So in fact, we have already begun to see how the two square objects are operating independently of each other. Let's make some further changes to the state of square 1. The list of methods includes some with the name move. For instance, move up, move left. Let's see what happens when we call those. Notice that not only does the view on the canvas change, but the values in the field shown in the inspector for square 1 also change. In fact, the logic is really the other way round. When we ask the square to move in a particular direction, the square changes the values in its fields appropriately, and then the square arranges for the canvas to show it in its new position. If we compare the inspector for square 1 with that for square 2, we can see that calling methods on square 1 has had no effect at all on square 2. This is an important point. Instances of the same class manage their state independently of each other. The instances are autonomous. Let's close the inspector for the second square because we aren't going to use it anymore. Indeed, we can also remove the object from the object bench in this case. But beware, removing a shape object from the object bench would not remove it from the canvas if it were displayed there. Let's create a triangle object now to go with the square, and then open its inspector. If we place the two inspectors side by side, we notice both similarities and differences. Both have similar position, color and visibility fields, but while the square has a size field, the triangle has a width field and a height field. Why the differences? In fact, the differences shouldn't really be surprising. We're dealing with objects created from two different classes, and the characteristics of those two types of shape are different. While the four sides of a square are all the same, so we only need to store one length, the three sides of a triangle may be all different lengths. But notice that since in our triangles we are only storing 2 dimensions, 2 of its sides will be the same length. This makes it an isosceles triangle. If we right-click over the triangle object, we can see that it too has a list of methods, including one to make it visible. It also has methods to move it left, right, up and down. Once again, calling these methods changes the state of the object, which is reflected in the inspector view, and we can see the changes on the canvas. For the next step, let's look at a slightly different type of method. Right-clicking over the square, we can see that there is a method called change size. But notice there's something different about this method when we compare it to the ones we've been calling so far. Immediately after the name of the method, enclosed between a pair of round brackets or parentheses, is the text int new size. All of the other methods we have called have had nothing between the parentheses. Let's see what difference this makes when we call the method. This time there's no immediate change to the inspector or the canvas. Instead, we're faced with a dialog that expects us to enter something. Reading the text immediately above the data entry area, it says, change the size to the new size in pixels. Size must be greater than or equal to 0. We are being asked here for how big we want the square to be. This is different from when we were moving the square. We were never asked then how far we wanted the square to move. The move methods simply moved the square by an amount built into them. Here that is not the case. We must say how big the square should be as a number of pixels. At the moment, the inspector shows us that the square is 60 pixels big. So let's make it twice that and enter 120 into the dialog. As we should have come to expect by now, the change is reflected in the inspector and the larger size displayed on the canvas. The value we specified for the size change is known as a parameter value. The change size method can only fulfill its task with that extra piece of information being passed into it. The meaning of the int new size part of the method in the method list is now clear. It tells us that when we call this method, we need to supply an integer value which will be taken as the new size of the square. Looking again at the list of methods belonging to the square object, we can see that there are several others that also take parameters. Let's look at the methods of the triangle object and see if this is also the case there. Indeed it is, but notice too that there's something different about the triangle's change size method. It has 2 parameters listed. Let's call it and see why that is. This time we're faced with a dialog that expects 2 parameter values. Reading a comment at the top of the dialog and the names to the right, it is obvious that we have to supply values for the new height and the new width. At the moment, the height and width are 60 and 70 respectively. So let's increase the height to 120, but leave the width alone. However, notice that we cannot simply leave one of the parameter values empty. We must still put the 70 in for the width, even though that won't actually change the current value. There is an important point here. If a method expects to receive a particular number of parameters, we must supply them all, even if we might think some are redundant. Once again, the inspector shows the new state and the canvas is updated. In this video note, we've seen that objects created from the same class have the same internal structure, but each instance maintains its state independently of the other instances. Changing the state of one has no effect on the others. We've also seen that objects of different classes typically have different sets of fields, simply because different classes represent different types of things with different characteristics. Some methods do not take parameters, they're simply called and they carry out their task. Other methods require one or more parameter values to be supplied. A full set of parameter values must always be supplied.